All right, okay, let's get it started then. We finished up to question number 6. Yeah.
Yeah, I think so.
Yeah, sparse model we were discussing here. Okay, so let's get started. The question number 7, which is theoretical, and question number 8 is all practical. Okay, so 7 is, does the dropout slow down training? Does it slow down inference, making predictions on the new instance? What about MC dropout? So inference time, we don't use dropout. So obviously, on a second question, does it slow down inference? I don't think so.
Yeah, I think you're right.
And does it slow down training? I don't think so either. Because it maybe expedite our training. What's the opinion?
I don't know either way, to be honest.
Yeah. How about you, Arto? Or welcome back, Gautam.
So I don't think dropout slows down training considerably. We add some operations, like we need to generate this dropout pattern and like do extra multiplications, but that's additive slowdown, which should be negligible with comparison to total computational complexity of the model.
So if I ask you, you mentioned we do some addition. So mathematically, how do we do the dropout mathematically within the layers? Do we multiply neuron by 0 or something?
Oh, I'm not sure how it's done, like internally in the frameworks, but I think that yes, we like generate a binary mask and then multiply by this binary mask. Maybe there are some like tricks to make it faster, but I'm not sure how it works. Maybe someone else can.
Anybody else want to pitch in about the dropout, how it's done, or whether it's slow down or expedite?
I'm not sure exactly how fast AI does it, but I thought Jeremy said, so if you set your dropout probability to be like 0.5, then like there's the probability that every node has, like every node can be turned off, I guess, yeah, by not sending a signal forward with a probability of 0.5.
Yeah,
right?
That's correct. Yeah.
But I don't know to comment on like the speed or what impact.
Yeah. So
yeah, like you zero out some neuron outputs. That's how dropout works. But how is that exactly implemented? Like if I would do it like drop out from scratch, I would use some random number generator and then compare it to a threshold, like this generated number, and then multiply like how it's called, element-wise multiplication to the output of this layer, and then you need to scale outputs to. You remember, like we need to scale outputs to make inference and training outputs on the same scale, because we like reduce the norm of the output by adding dropout.
Correct. So that means like we have to do more operations now. One is to the as you said, like looking at the threshold and multiply a neuron by 0, and then the other operations what we are doing is scaling out the training because we are dropping it out.
Yeah, but
So-
those operations are relatively fast. So I don't think like you really have that's an important decision in terms of training speed, whether to add dropout or not, because like
Yeah.
that's additive slow down. So like dropout is much benefit from the dropout is much more important than this slowdown which we get. I'm not sure if it's even noticeable. That would be interesting to try out, like to time this some network with and without dropout.
Yeah, that's correct. Yeah. I think in this exercise he hasn't said it dropout, but did he? No. I think he did here regulation model with alpha dropout. So I think there is one where we can notice the time. Anyway, so and then the last question is, what about MC dropout? What is MC dropout, by the way?
That's Monte Carlo dropout. That's it's introduced in this chapter when you use dropout at inference and you generate multiple predictions with dropout, and then you average over those predictions.
Oh, so you're saying the dropout is getting used during the inference,
right?
That's called MC. Like that's a Monte Carlo dropout.
Right.
Okay, I need to go back and then read this. I totally skipped it, or I don't remember it doing it.
In general, it can improve your accuracy somewhat, and it is useful to get like estimation of how confident the model is in some predictions, because if you do these predictions with dropout, and those predictions are somewhat noisy, and for those examples where model is less confident, you will get more variation in these predictions. And so when you have this, you do multiple predictions, and then you can estimate this variance of the prediction. So you like have an estimate how confident the model is about certain example.
Okay. Okay, thanks for that. Anybody else want to ask any question or feedback?
Yeah, and so about this question, like it slows down inference substantially, because like you need to run inference multiple times to use this technique.
So for the MC dropout, you're saying we are going to do inference not once, but we're going to have a number of times, and then we're going to take a average value or average value of inference?
Right. Yeah, we generate multiple predictions and then average them.
Okay, that's the reason it's going to.
So in Monte Carlo dropout, it means that you won't get the same result for a particular data point every time, right? Every time you might get slightly different results.
Yeah, right. That's just like at training, you know, dropout is random, and you do inference with dropout with active dropout. That's all about Monte Carlo dropout. But then you get this noisy predictions. Like you use, you know, when we train a model, usually you see that training loss is worse than validation loss. And that's usually due to this dropout we use at training. So and if we do Monte Carlo dropout, we use that would be similar to using ensemble. Like with dropout on, we have like multiple models. Like every model uses a subset of the weights we have in our like this original model. So yeah.
But it's not that common, right? Monte Carlo dropout.
I'm not sure. Probably it's used mostly to estimate the like confidence of the model. Because what I observed, but I really tried it only when I was like playing with this homework, and the accuracy didn't improve like really much, but you can get this confidence interval, like variance across different predictions, and I think that might be very useful in some cases. So FastAI has a callback for Monte Carlo dropout, so I think it's like indication that it is used and it's like useful. Maybe in some cases you can substantially increase your accuracy, but generally I think the most important thing is that you can get this confidence of the model.
Okay, thanks.
Cool. Maria, you wanna read out the answer, please?
Sure, yeah. Yes, Dropout does slow down training, in general, roughly by a factor of 2. However, it has no impact on inference speed since it is only turned on during training. MC Dropout is exactly like Dropout during training, but it is still active during inference. So each inference is slowed down slightly. More importantly, when using MC Dropout, you generally want to run inference 10 times or more to get better predictions. This means that making predictions is slowed down by a factor of 10 or more.
Wow. Wow.
So dropout doubles your training time. Is that what it says?
Yeah, I think so. Yeah.
Twice, yeah.
That's a bit too excessive.
So maybe
that's interesting. I would like to like test it and see if it's really so.
So it does not talk about like how many layers you keep the dropout, right? It just says dropout slows down training by a factor of 2. Does not say for how many layers you have the dropout.
No.
But that probably is, I think, like for a likes. So you have one model, you have dropout, no dropout, and then another one you'll use after every, I think, every step in a way. So you're getting into that if we just introduce just tiny bit of a dropout. Is that what you inferring to? Not after every layer. Is that what you mean, Gautam?
No, I'm saying obviously the amount by which it slows down depends on how many layers dropout is there, right? If you keep it for all layers, it probably be much lower than if you keep it for just one layer. So I think that should be mentioned along with with this, because you can choose like how many layers you want to keep dropout.
Dropout, yeah. Okay, so interesting. Let's move on to the practical, the question number 8 now, if you don't mind. But I will encourage everybody to do it. What we will do is maybe set up 5-7 minutes to go through it, and then maybe give it a run. I think we still have 40 minutes. We can do maybe ABC up to C. It takes some time to train. Then we can have a discussion as well. What do you guys think? Or do you want to just walk it through on my screen?
I think we can spend some time on it individually, and yeah.
Yeah. So I would say maybe get ready and then start doing it. And let's do first question. I'll read out first question. So, and then we'll do the setup. Basically, if you look at the book, the book has the answer actually. So that's 11 training deep neural networks. So you go to last, he has given the answers. So all you need to do is just a setup, and then you probably need these libraries to add in here. Otherwise, you have to go all the way. And that's pretty much it. And then you can start running it, and then we can come back and then have a discussion. So let me read first. So practice training a deep neural network on a CI-FAR 10 image set. Build a deep neural net with 20 hidden layers of 100 neurons each. That's too many, but it is the point of this exercise. Use the he initialization and the LU activation function. So let's do this. First one, make a model, get the data, run the model, and another thing which you gotta do is in this, this will error out. If so, you need to add this this line just before this. In the notebook, you have just only this, but you need to add this load extension Tensorboard. Then your Tensorboard will come up after that training. So let's spend another 5-7 minutes to run it, and then get back, and then we walk through the whole model again for a question number 1. All right. Okay. Hopefully you guys have set it up. So I think the training is still going on. So let's the Epoch running. If you guys have started already, we can start discussing about the how the model is set up. Agree? You with me?
Yep.
Okay.
Sorry.
Yep.
Okay. So so he has asked us to create the sequential model with the 100 neuron in each layer, and then we have to stack the 20 layers of it. And the activation function, he is using the LU, and the initialization is Hall normalization. So that's specified here in here. So model created with the 20 layers of dense layers with 100 neurons. And the input image is going to be a 32 by 32. I think CIFAR 10 dataset is handwritten digits. Overall, we have a 60,000 images. We're gonna keep 50,000 for training and 10,000 for testing. So once we have built this, the last layer is going to be a softmax for the 10 classes 0 to 9. So that's added. Oh, I already have added, so I didn't need it. Optimizer is Nadam with the learning rate of 5e minus 5. So he has tried out different learning rates, and then he finally stopped with this. So we're just gonna steal his idea on best learning rate that we are using down below. And the loss is sparse categorical cross entropy. As we discussed last time, that's the loss when we have multiple classes. That's what we use. Optimizer defined up here. LU optimizer is, oh, sorry. Optimizer is Nadam, not LU. And the metric we are looking is accuracy. So this is to load the data set into X train full, Y train full, and then from X train full, we will extract first 5,000, which is first, okay. So I think validations are the last, first 5,000 are for validation, and from 5,000 onwards, 45,000 records we have for training. So we're going to train on 45,000 and validate on the last 5,000. So that's what we have. So this is the interesting part, which I probably have few questions. Basically, what he's trying to do is, one is like getting up this Tensorboard up and running, plus there is early stopping. So he has keras.callback early stopping, patience of 20. I'm assuming 20 is the 20 epochs. After, if your validation keep on going up, you'll stop it. Correct me if I'm wrong.
The validation does not go up, right? I mean,
Validation
if the loss, sorry. Yeah, if the loss is just decreasing for 20 consecutive epochs, yeah. Then it will stop the training, and it would take the model prior to those 20 epochs.
So if the loss stop going below the point, and then it will keep on checking for 20 epochs. Is that correct?
So if the losses has not dropped for 20 continuous epochs,
Mhm.
that means it's obvious that it is getting worse and worse. So it would stop, and then it would take the model which was at the epoch prior to those 20,
Yeah.
just before
So,
those 20. Yeah.
so which loss? The validation loss?
Yeah. Validation, obviously. Yeah.
Validation loss. Yeah. Okay. And so it's going to take the model for exactly the 20 epoch before where it's stopped going down, or would it look further down the line somewhere? Oh no, actually,
I think it's the exact one before this 20. Yeah.
Okay. Okay, that's good. Then we have a model checkpoint, Keras.callback.model checkpoint. So say best only true. What does this mean? This is the name of the model we are storing. So this is the model we say if we just discussed like 20 epoch before, whatever model is the best validation loss is giving to us, that's the name of the model and it's saving it. Is that correct?
Yeah.
Okay. So come on. All right. And we have run index 1, just starting with 1, and I think it keep on increasing with every epoch, I'm assuming. Increment every time you train the model, and run log directory in a current directory. It will create another, I guess, subdirectory, and within subdirectory, it's gonna say run underscore index 1, 2, 3, 4. So I'm not sure whether it's related with the, actually, let's check. How do I check? If I go here, and that's the my CIFR10 logs, and within it, it's a run 01, and it's a train. Okay. So, okay, so it looks like not an epoch. It's number of time you're doing the trainings. So it's going to create this a subdirectory under the my CIFR10 logs called run underscore whatever the index number is. However, the index is how many times you run the training. So it's not the epoch, if you know what I mean. That's, yeah, and under it, it's creating train and validation and saving the model. So in a sense, if I run this training multiple times, they run it. If I don't reset, I'm resetting it to 1. So it's always going to overwrite. Anybody has any idea what this run index is doing? Is it related?
Yeah, that's doing what you said, but you need to increment it manually to make it work.
So in a sense,
if you do second run, you have to manually increment run index.
Yeah. Okay. Okay. Thanks for confirming. So that's your run directory, and then this is just the calling the Tensorboard. We call the Tensorboard with the location, and we have callbacks of early stopping, model checkpoint, and Tensorboard. And that, I guess, we pass in here, callbacks. That's what we are passing, 3 callbacks in here. And now let's see if the model has, okay, so model has finished. So I got in a 32 epoch, I think. My validation loss was 2.03, 2.3, and validation accuracy of this. Does it sound good to you guys? Like, what are you guys getting? But it's still, let's see what it says here. Now mine is, I think something wrong happened here. Mine accuracy is not even 0.1. He said it should be 47%. I didn't get even 10%. And I didn't change anything. That's quite interesting. 5,000 samples. The first time when I ran, it was not that bad. So let's discuss this guy here. So actually, I'm gonna. This is the run which I got. It's a batch now. Sorry, I thought I got this. So that's the. There's one more here. Is your training finished? Are you guys getting the Tensorboard like this? So interestingly, it creates the directories here, as I was saying before. I think it's saving all your runs here. Like I ran it before coming in here. So for the batch norm, it created a subdirectory and it created the logs in here. So this is quite interesting to see on your machines here. And if you go back here, these are the subdirectory you will see here, and then you can switch it on and off whatever you want. So for our first question which we ran, that's the epoch accuracy you see here, and I think it's around in here where our loss start going up, which he was saying first time when I ran. So this is where he stopped, like I think 47, 49. So the blue is the validation and the orangey is your training. So training accuracy keep getting up and up, but the validation is stopping in here. And same with the epoch loss. Your training loss keep on going down, but the validation loss start getting plateauing, and then it start going up. You see here. So I think it stopped here. That's the best model he got in here. So it's quite handy to see. Anybody else got the same result? Or I need to run it again. Sorry. Any question on this? Okay, so let's move on to the next question then. We did the evaluation here. So we, using a NADAM optimization and early stopping, train the network on a CFI or 10 data set. You can load it, blah, blah, blah. Load it data set by this, we did. The data set is composed of 60,000 images, 50,000 for training, 10,000 for testing, and with the 10 classes. So you will need a softmax output layer with the 10 neurons. Remember to search for the right learning rate each time you change the model architecture or hyperparameter. Obviously, we didn't do it, but we can retrain it time and again with the different learning rates. However, I think the last question is here. He say one cycle scheduling, which will give us a good learning rate. So we can come back to here, try different, see how it works. Anyway, once we reach here, then we'll tackle with this this part of the question. So second portion is now try adding a batch normalization and compare the learning curves. Is it converging faster than before? Does it produce a better model? How does it affect training speed? So Next one is, now one of the issue with the next question is, it took me around, I think, 20 minutes when I last ran. You'll get the accuracy slightly up, not too much up. I think you get around 55% of accuracy. So maybe you want to give it a go now. We have 15 minutes, but what we'll do is we'll walk through this model, and then we probably stop after this walkthrough, and then we'll join the class, CNN class. Does that work for you guys?
Yep.
Okay, so if you have finished the last one, kick off this one, and I'll give you maybe 5 minutes to just go over it, and then we reconvene in 5 minutes just to walk through different steps he has taken in here. And they're almost same, but no harm to go over it again, and then we're done, I guess. Let's take 5 minutes. Okay. Okay, so let's finish this off. I'm still on a 12th, 13th epoch. Question for you, any of you. Could anybody confirm what was the timing they had for a fast model training for each epoch? Mine was on average 15 to 16 seconds. He mentioned 10 on his PC, so I just wanted to see what you guys are getting, more or less. Anyone?
For the one without dropout, for me, it's like about 18 seconds per epoch.
The first one which we did. Yeah,
Yeah.
mine is between 15, 16. Okay, I thought I'm worse. And what are you getting for the next one?
Oh, mine is still running the first one, so I don't know.
Okay, I got around 27, yeah, 27, 28 seconds per epoch. So that's going to take around 25 minutes, I think. It took 20 minutes last time. So it's probably going to take 20, 25 minutes now. Anyway, so let's walk through quickly the model itself. So the model is to introduce the batch normalization. So we have the flattened layer, 30 by 32, and then we have a batch normalization layer added in here. One thing which I didn't understand, is this the 32 by 32, comma 3? Is 3 is the batch size?
3 is the channels.
3 is the
The
channel.
number of
Here's
channels.
the
Yeah.
colored picture. So one thing which I was looking is there is no batch specified anyway.
Yeah, it should be. I mean, it should work for any batch size, right? You are just having layers. Your batch size can be 1 or 1,000. It should still work. So layers are just what it will do to each example in the batch, or to the batch as a whole.
Okay, so
It should not be specific to the batch. Yeah, batch size.
so you're saying the batch normalization is specific to the batch.
Yeah, I mean that's just how it will normalize the
Yeah.
data that you have. Yeah.
So
But it should not be specific. Nothing. No, the layers are not specific to the number of the batch, right? No, the batch size.
so when we don't specify the batch, so it's going to consider the whole data set as a batch.
No, it's whatever you pass to the model at one time. So usually you pass maybe 32 or 64 at a time. So it will normalize with those 32 at 32 data points.
Yeah, so that's the question. Like, we are not specifying what the batch size, where there's 32 or
It should be there somewhere. Let me just see.
Yeah, it simply operates over batch channel, which comes first. So doesn't matter what the exact batch size is. It will compute averages over a whole batch.
so if you haven't if we didn't give a batch size, would it take the whole data set and then
No,
it,
it will compute batch statistics, like how batch norm operates. It normalizes the input batch, and then multiplies it and scales it and shifts it by some learnable parameters. And at training time, it computes a batch that it uses whatever batch size you have. It computes statistics over that batch. We need mean and standard deviation.
yeah.
So also it stores running averages of the statistics to use it at inference time. So when you run inference, it uses this average statistics over all batches. But at training time, it computes statistic for every batch separately. Like you have 32 images, so it will run batch normalization over these 32 images.
Okay, yeah. Yeah, so the only confusion I had was I didn't see the batch size in here. This is the shape of the image, each image. And then what I couldn't find is where is the batch we are specifying. So if we are not specifying a batch.
Yeah, you don't need to specify the batch. It just will do it over whatever batch size you have. It, the batch channel comes first, batch dimension comes first, and it will use this to calculate batch statistics.
Here the default is 32, Dinesh, so it will take 32 images at a time. So when you do model.fit, it will automatically just pass 32 images at one point of time.
Okay, 32 is default one. If you don't specify, then it takes. Okay,
but the 32 that's given in that input shape is the dimension of the image, not the batch size.
Yeah, so this is the dimension, but default is, where do you specify? Oh, you specify
in the fit model.fit here.
Fit here. Okay. Okay. I don't think I can. Mute yourself. Not sure. Okay. All right. Is it? No.
Animals. Animals. Animal.
Okay. Okay, so that's the only thing different in this model. We have batch normalization defined after the flattening, and then again after the dense layer, and the rest is pretty much same. There wasn't any difference. So obviously what he discusses, we're going to take more time. It's going to take more time to run the batch normalization, obviously taking more time. However, it says that it's going to converge early. So let's quickly go if I can. That was the batch normalization, validation, and train. And we have 55 here. I'm not sure how to. So we have a training accuracy going up, and then it's going, loss is going down. However, the validation is plateauing. Well, in here, I would say around here as well. It start converging, the loss stop going down around here. So you can say that's probably start converging around somewhere here, I guess. And if you're looking up here, we are on the same mode around here. The rest is same. So yeah, it converged between 25 and 30 epochs, I would say. Yeah, and then if you look, if I add this into a mix, it was still going up here. We converge here like after 50 epochs. And that's the point he's trying to make, that if we have a batch normalization, we converge quite early. And same hold true. Well, I'm not looking even training, just looking at the validation loss and validation accuracy. Okay, so that's all I have. I think we can probably stay in the same class Arshad will join us and then we'll take it from there. Until then, we can discuss anything if you want. So next Wednesday, we'll meet again. It's going to be hour and a half, and we'll try to go through these again. The question number, we will start with the D, where we're gonna replace LU with the CELU, and a key normalization going to be replaced with the LeCun, and then see what difference it makes.
You mean Monday, right?
Oh, Monday, sorry. Yeah, Monday. Monday. So I think the consensus is that not to meet on a Wednesday for homework, just to meet on a Monday for hour and a half. So that's fine with me. Yeah, but it's I'm finding it very interesting to work with everybody to get it done. Otherwise, we'll just forget things. Okay, Arshad is here. Over to you,
Thanks,
Arshad.
Anish.
Thank you,
Hey
Dinesh.
guys.
Hi.
Yeah, cool. It was an interesting discussion you had. It's a shame, unfortunately, I can't attend them. But I'll try and see if I can. Do you guys record them? They should be recorded, shouldn't they, automatically? Yeah, they're being recorded.
Yeah.
I might watch them. How is everyone?
Good.
Cool. Now, so we're going to go back a little bit because the guys on Sunday, I think they must have been ahead last week because we finished before the pooling chapter last Wednesday, and they seem to have gone straight for the networks section when I joined on Sunday. So I think we missed the pooling bit, so we should do that. And then yeah, and then if we look at the CNN architectures section and see if we can finish that today. So the idea is if you guys could start reading from the pooling layers chapter, and then see how far you can get in the CNN architectures chapter, because they got to ResNet in the on Sunday, but we'll see if how far we get with that. Is that okay? Or does anybody have any questions?
Yeah, fine with me.
Sounds good.
Cool. So we'll catch up at say 45 minutes past, and yeah, I'll speak to you at that point.
All right, talk to you then.
Thanks then. All right. Bye.
Thanks.
Oh, hey Dinesh. Hey Otto.
Hey.
How's it going?
Good, good.
Cool. Otto, you seem to be really getting into NLP. So is that, are you going to try and specialize in that, or are you still open to anything?
Yeah, well, I'm still open. Yeah, I like what I'm doing now, but you know, you never know before you try. So I would like to try to go deeper into reinforcement learning, maybe something like on the edge. So I have more like smooth transfer, but actually like I still feel there is a lot to learn from NLP, and
Yeah, it's really interesting. I mean, I think I mentioned to you I was doing this competition at the weekend, and that was kind of old school because they were really interested in clustering, and they were using a lot of the scikit classifiers. One or two of the guys who were in the competition did use BERT, but yeah, it seemed to be. So I was like, oh, I got to learn that because I've been kind of ignoring it because I thought BERT and you know, stuff like this would be, you know, a lot more useful. But actually, some of that clustering related stuff would have been a lot more handier.
Yeah,
it's
so
interesting to take to participate like some real world tasks competition, and it like brings you closer to reality than reading a lot of papers.
Yeah, definitely.
yeah, just to add, we like, you know, the NLP, the Kaggle competition, the Kaggle class on, I think it's on a Saturday after the CNN.
Yeah.
So for the last couple of months, we have been using this NLP for a Quora questions, and
Yeah.
the winner on that competition 4 years back was XGBoost. So we said we took their kernel, we ran it, and then we got a score around like 0.25 or something, or
Yeah.
it's or maybe 0.1. And then
Yeah.
afterwards, people went away. They start using BERT, a sentence encoder. Nowhere even near we are that score.
Yeah.
People have used different techniques. I think one of the Steve is getting around 0.3 with the BERT, while the winner with the XGBoost was, I think, 0.15. So,
All right.
so it's a very interesting. Like old methods are like still the winners.
Yeah. Yeah. Cool. So I think we've got everybody we were expecting back, so we can probably start.
Yeah.
And interestingly, the first sentence on this, which says, once you understand how convolutional layers work, the pooling layers are quite easy. And actually, I'd misunderstood how the convolutional layers were working because at the weekend, you know, the guy was sort of going through, I think, Google LeanNet or something like that. And all of a sudden, I was like, I don't think I understand how convolutional layers are working. So I thought I would just kind of explain what I think is going on. And then maybe, you know, you guys, if, you know, you agree or not.
Yeah.
So actually, we'll go for a second to, let me see if I go to LeanNet, it's architecture. So for instance, here we've got an input of 32 by 32. And then it's only got one channel in it because you know, it's a black and white image. And then after the convolution, we're going to have 6 channels available. And then, okay, we're doing some pooling here. So let's start here. So after the pooling, we've got 6 channels. And then we're going to expand them to 16. And it was all a question of how is it expanding the 6 to 16? Because I didn't understand how that, you know, because this was potentially 6 dimension. If you imagine this is 3D, so there's 6 of these stacked one on top of another. How does it go from the 6 to the 16? So, okay, so what it seems to do is we want 16 features at this stage. So what we're going to get is basically 16 feature maps, and each feature map is going to be computed by a kernel of size 5 by 5 going across this image, but it's got a depth as well. So this is not just a 2-dimensional kernel. This is not, I mean, even though it says 5 by 5 there, that is just like the top level of it. It's going to have another dimension, which is 6 deep, so that each feature is actually going to be like a cube being applied to these guys. So you can imagine that let's say we're only looking at feature 1 in this layer. Well, the way that's going to be computed is going to be a 5 by 5 kernel, but of depth 6. And then that whole kind of cube worth of calculations is what's going to be put into each, into say one feature map, and then there'll be another one which is going to do similar but with different weights. And then we'll have sort of 16 of those. So that's where you're getting, as soon as when you go, I mean, for instance, this guy here, if you just looked at the kernel, it's 4. So it would have had, say, 4 weights. But because it's being applied to 6 layers, so that's 24 weights potentially here. But as soon as you go to 5 by 5, that's 25 weights there, but then multiplied by 6, which is what? 25 by 6 is 120. That's 150 weights. So this is why you need a lot more memory as soon as you're going to do bigger kernel. Did that make any sense to you guys? That this expansion from 6 to 16?
So you were saying 5 by 5 kernel means 5 by 5 by 6 kernel.
That's right. Yes. So
Okay,
it's like a cube of data.
Yeah. So then you're going to apply on 6 layers. So when we say average pooling is 6, if you come down further, like let's say C1 is convolutional 6. So we applied 6 convolutional, and afterwards we applied the average pooling, but we still have a 6 feature maps. Yeah, that's the 6 layers. We still have it.
Well, here we had 6 layers.
Yeah.
But here we'll have 16.
How did we reach from 6 to 16?
Okay, so this is the bit where okay, so what's going to happen is that when you do this this operation, it will create 16 layers for you. And then the data in the 16 layers is going to be created by using a 5 by 5 kernel, but of 6 depth. So the first layer of the 5 by 5 will be applied to the first channel in here. The second layer of the 5 by 5 would be applied to the second channel, and third, fourth, fifth, and then the whole thing would be added together to compute the one value that you would have gotten if you just applied like the 5 by 5 just to like a one-dimensional thing.
Okay.
And so this is how you go from 6 to 16, is that as soon as you've done, see, you will have gotten 16, but the data that's filled in is by using this cube of weights, the 5 by 5 and of depth 6, because you need to apply a 5 by 5 on each one of these 6. So on layer 1 of the 6, layer 2 of the 6, layer 3, layer 4, layer 5, and layer 6, and then add all that together to make one of these guys. Does that make sense?
Yeah. So on 6, okay, and then so let's say you have done first time, and then you created one layer out of a 16.
Yes.
For the second layer, you're gonna have a same kernel applied again.
Yes. So again, 5 by 5 by 6, but with different weights, because the weights are all going to be initialized randomly and then learned.
Okay, so that's the difference. So you apply the same weights, however, you're applying the same kernel, however, the weights are learned, and then they are randomly initialized. So we're going to apply 5 by 5 16 times to these 6 layers, because weights are learnable, so it's not going to be same. So my confusion was that you're applying the same kernel to 6 layers. What's making it is different? But as you said, weights are making it as a different.
That's right. Yes. Yeah, this is a bit because when we were talking last week, I assumed this was only a one-dimensional thing. Sorry, this was just like a rectangular patch of data. Because I don't know if you saw the image, the example they gave earlier in the book. It looked flat.
Actually,
you just had a 5 by 5 walking across the image, but actually it's a 5 by 5 by the number of channels down here. So if it's red, green, and blue, for instance, it would be a 5 by 5 by 3. Because it would be applying it to the red channel, the green channel, and the blue channel, doing a whole calculation and then generating one.
No, but you said in the input we have just one channel. So this would, when you say a 5 by 5 by 3 or the depth come into a picture only when there is 3 channels.
Well, depth is sort of always, I mean, this, for instance, here, the depth is 1. So so this is going to be a 5 by 5 by 1.
Yeah.
But obviously, ignore the pooling because the pooling is doing something slightly different. But any convolution layer, it's going to be whatever the previous depth was times whatever the area of the kernel is. So that's how big that kernel is going to be as it's being applied.
Okay, so in a sense, the 16 is the output. It's not automatically coming out from 5 by 5 by 6, but it's like we wanted the 16 convolutional layer to be created.
Yes, that's
we
right.
Specify.
Yes. So yeah, I mean, and that's going to explain sort of how some of the networks are working, because as I said, I couldn't understand how it was, how this thing was expanding from 1 to 6 to 16 to 120, like what operation was being done. Yeah, so, but we'll get back to pooling layers now because we've slightly digressed, but I thought it was important because last week I misunderstood it and I thought I probably didn't explain it to you guys what it was doing. Okay.
Thanks for that.
Yeah, cool. So pooling layers are a bit simpler. So their goal is to subsample, that is to shrink, or well, it may shrink or it may not, but we'll see. But you're in theory doing a very simple calculation on the input data. There's no weights here. So there's a couple of different types of pooling. There's like max pooling, average pooling, and global average pooling. So yeah, and so the main purpose of them is to reduce overfitting. So this is kind of, you're losing quite a bit of data basically when you're doing pooling. I mean, if you're max pooling, you're only taking the maximum value in that area, and average pooling, just taking the average value. So you're losing quite a bit of data of information, and that is going to stop the overfitting. So just like before, because pooling is being applied like as a patch on top of the channel that you're working on, you have to specify its width and height and stride and padding type, because all of those sort of come in. As it says here, pooling has no weights because all it does is apply an aggregation function on the inputs, such as the maximum or the mean. And I mean, the most common one we've all come across is the max pooling layer, which is taking the maximum value in the small patch. So for instance, if you've got a 2 by 2 pooling kernel, then in any small 2 by 2 rectangular area, it's going to take the maximum value in there and compute that as the output. So yeah, this is where it says only the max input value in each receptor field makes it to the next layer, while the other inputs are dropped. Yeah. Now, if you use a stride, like for instance 2, then what the effect of this is going to be is that not only will you be taking the basically you're going to reduce the size of the image depending on how big the stride is. If the stride is 2, then the image is going to be half the size as it was originally. And yeah, so it says rounded down since we use no padding. Does that kind of make sense what pooling is doing? It's kind of taking either the average value or the maximum value in a small area and then outputting that as the result. And if the stride is bigger than 1, then it's kind of the effect of that is going to be is to compress the input, compress the size of the next the channel that you're going to generate. Is that okay, guys?
Oh yeah. So the kernel is going to be always a square.
It doesn't have to be square. We normally specify it as square, but there is a notion that there is an X dimension and a Y dimension to it.
But you can do maybe 1 by 2 or 2 by 1.
Yes, yes.
You can, in theory.
Yeah, yeah. The code allows it. Yes, so unlike the convolutional layers, a pooling layer works on every input channel independently. So the output depth is the same as the input depth. So whereas convolutions were working across the full depth of your input, if it was, for instance, RGB and there were 3 layers, then convolutions are working on all 3 at the same time. Pooling layers work on 1 channel at a time. So it really is this 2-dimensional data is looking at. There's no depth for where pooling is concerned. And so one of the effects that pooling has is to introduce a level of invariance. Because you're taking the maximum value, no matter whether it's here, 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 or here, then in theory, you've got a little bit of invariance here in that the data, if the data was slightly shifted and the maximum value is here, the pooling layer will still generate exactly the same thing. And that may be of interest to you, or may be useful to you in your application. And here, depending on what the weights are, it could be that you've got 2 images which are slightly different, but actually the output of the pooling layer is identical because you've got this small translational invariance. Yeah, so this is where this is by inserting a max pooling layer every few layers in a CNN, it is possible to get some level of translation invariance at a larger scale. Moreover, max pooling offers a small amount of rotational invariance and a slight scale invariance. Such invariance, even if it is limited, can be useful in cases where the prediction should not depend on these details, such as in classification tasks. Yeah, so that's one of the other effects of pooling is that you're getting some of these slightly scale and rotational effect. It's because rotations within this area here won't have an impact on the output of your pooling.
But in general, when you rotate a picture, it's not going to rotate the pixels. It's the whole picture is rotated, let's say 90 degrees. So the
yeah, I mean, it all depends. I mean, I guess what they're saying is if there's a small amount of rotation where, for instance, a pixel here goes to a pixel here, then your max pooling will still take care of that, because if it was going to output, if that was the maximum value before, and this is the maximum value here now, it will still be exactly the same in terms of your pooling. So it's very, very limited amounts of rotation, unless your pooling layer is obviously much bigger. If it was a 5 by 5, for instance, then anything happening within here, so long as the maximum weight was the same, it wouldn't have an effect on it. So yeah. And they've got some examples of where, slight changes. For instance, here's a small translation. The output is exactly identical. Whereas if there's a slightly bigger translation, then now the output is different. So it's only limited amounts of translation that will result to you in the same output. So there's a little comment here. First, it is obviously very destructive, even with a tiny 2 by 2 kernel and a stride of 2. The output will be 2 times smaller in both directions. So this area will be 4 times smaller, simply dropping 75% of the input values. And in some applications, invariance is not desirable. So if you really did want to tell the difference between these two, then including pooling would actually not help you, because it wouldn't be able to tell the difference between those two. So the goal in this case is equivariance, not invariance. Small change to the input should lead to a corresponding small change in the output. Okay, so what's this? Text semantic segmentation, the task of classifying each pixel in an image according to the object that pixel belongs to, which we'll explore later in this chapter. Obviously, if the input image is translated by 1 pixel to the right, the output should also be translated by 1 pixel to the right. The goal in this case is equivariance, not invariance. A small change to the input should lead to a corresponding small change in the output. Yeah. So if your task was this thing, semantic segmentation, which is basically tagging each pixel with what object it belonged to, then having invariance is actually not a good idea, because you would be, in this case, you'd probably be indicating that these pixels were the ones that were this shape. Whereas maybe the image you were given is actually this one, so that you would have incorrectly identified the pixels that were being tagged. So you've got to keep in mind what exactly you're trying to do, and it's worth bearing in mind that pooling could have some of these kind of strange side effects for you, depending on what you were trying to do. Then they give a small TensorFlow implementation. So this is the layer, the MaxPool 2D layer, and by default, this is a 2x2 by specifying the pool size as 2. And they're saying, there's an alternative, which is the average pooling layer. So just use average pool 2D instead of max pool 2D. Okay, and there's a comment here, average pooling layers used to be very popular, but most people use max pooling layers now, as they generally perform better. This may seem surprising, since computing the mean generally loses less information than computing the max. But on the other hand, max pooling preserves only the strongest features, getting rid of all the meaningless ones. So the next layer gets a cleaner signal to work with. Moreover, max pooling offers strong translation invariance than average pooling, and it requires slightly less compute. Okay, note that max pooling and average pooling can be performed along the depth dimension rather than the spatial dimensions, although this is not as common. Yeah, so you could average across the channels depth-wise rather than within a particular channel. But yeah, as they say, I've not come across anybody using it. Okay, so yeah, this is what they mean when they say depth pooling. So across the feature maps rather than within a specific feature map. Keras does not include the depth-wise pooling layer, but TensorFlow's low-level deep learning API does. Just use the TFNN max pool function to specify the kernel size destroyed as 4 tuples. Tuples are 4 sides. The first 3 values should be 1 by 1 by 1. This indicates that the kernel is stride along the batch. Height and width dimension should be 1. The last value should be whatever kernel size and stride you want along the depth dimension. For example, 3, this must be a divisor of the input depth. It will not work if the previous layout was 20 feature maps, since 20 is not a multiple of 3. Yeah, so there is a way of getting depth pooling using this function, if you ever needed it. Okay. So so there is one other one worth knowing, which actually I think Google Linet uses, which is global average pooling. It works very differently. All it does is compute the mean of each entire feature map. It's like an average pooling layer using a pooling kernel with the same spatial dimensions as the inputs. This means that it just outputs a single number per feature map and per instance. Although this is, of course, extremely destructive, most of the information in the feature map is lost. It can be useful as the apple layer, as we will see later in this chapter. It doesn't seem like the most useful thing, but actually it can be useful because you can take the output of that and feed it into a classifier. Okay, so and that's the global average pooling 2D. Okay, so this is a reduced mean. Okay, so you can implement it using a mean function of some sort on a kernel. Okay. Does anybody have any questions related to that before we move on to the CNN architectures?
I'm good.
Okay, so moving on to the convolutional network architectures. So typically convolutional neural network architectures stack a few convolutional layers, each one generally followed by a ReLU layer, then a pooling layer, then a few more convolution layers, and then ReLU layers, and then pooling layers, and so on. So this is kind of the overall architecture, is kind of stacking these kind of layers on top of each other. The image gets smaller and smaller as it progresses through the network, but it also typically gets deeper and deeper with more feature maps, thanks to the convolution layers. At the top of the stack, a regular feed-forward neural network is added, composed of a few fully connected layers and ReLUs, and the final layer outputs the prediction. For example, a softmax that outputs estimated class. So here we've got 3 channels as input. You're getting a certain number of feature maps, and pooling is keeping the same level. But then you've got more feature maps here, more pooling, and then these dense flat layers, which are going to act as your fully connected layers, which help you with your classification. So that's kind of the overall architecture. So there is a little comment here. A common mistake is to use convolution kernels that are too large. For example, instead of using a convolution layer with a 5x5 kernel, stack 2 layers with 3x3 kernels. It will use fewer parameters and require fewer computations and will perform better. Yeah, so even with only a one-dimensional thing, a 5x5 kernel will need 25 parameters, whereas a 3x3 will only need 9. Even if you use 2 of those, that's still only 18. Whereas that one was still 25. And if you add in the depth as well, then that's going to increase the size of the number of parameters that needed for that by, much bigger than using 2 smaller ones. Okay, one exception is for the first convolution layer. It can typically have a large kernel, for example, 5x5, usually with a stride of 2 or more. This will reduce the spatial dimensions of the image without losing too much information. And since the input image only has 3 channels in general, it will not be too costly. Yeah, so what they're saying is probably the image is, most images are too detailed. So even if you compress them down, you're not going to really lose like a monstrous amount. At least initially, but once you've started selecting features, if you start applying really huge kernels, then you potentially will be losing a lot more information. But the good raw image, you could compress that down and still sort of be okay, which kind of makes sense. I mean, even if that image was like halved, I could still see so that building and a few of the features in here. If the main aim was to recognize the building, I could probably still do it. Okay.
Quick question on this architecture. The last fully connected layer. I can understand the last fully last layer, but what are the purpose of this last 2 layers in a fully connected layers? What's the value add in this architecture?
You mean these two, the ones at the end?
No, the one before these 2, yeah.
So that one and that one.
Yeah.
Okay, so here we're going to say perhaps I have hundreds of different features, yeah? So this is what the convolution is bringing in out for you. Mm-hmm. It's highly unlikely that you could just take a linear function of just the features in one layer and compute the output. What you probably want to do is to combine these features into other features, which is what this fully connected layer is going to do, and then combine those features into even bigger sets of features, which is what that's going to do to you. Because remember, what convolutions are doing is just identifying features. They're not merging the features for you. All they're doing is finding lines, shapes, various features in the input. It's the dense layers that are going to combine all those features in kind of meaningful ways to give you the actual output. So you probably do need a reasonable kind of sized, fully connected network to combine all the input features that are of interest to produce your final output. That's my explanation. I don't know, Arthur, what do you think?
Yeah, I agree. Those layers are just to introduce like more computation to the network, so it can combine these features in various ways. Also, you usually will add dropout between these layers. So when you have dropout, some features will be excluded from training, and it will have to learn like to predict the same class from different kinds of features. For example, if we want to identify this building on this picture to assign it to some class, we can decide, okay, we have a roof here, and also we have like this floors. So I think it will make network somewhat more robust to different kinds of features which correspond to each class.
Yeah.
So why not use the pooling rather than fully connected?
Well, pooling is remember it's not applying any kind of complex function, is it? It's just averaging, or taking the maximum value. Yeah. If you just put that straight into, say, some sort of a softmax, it's. I mean, you could compute that there is a certain feature in the input, but it wouldn't tell you what the total image was. I mean, that would be kind of my explanation of it. The pair pooling is still only isolating specific aspects. It's not combining different aspects to produce you something more interesting.
Because you're going to work, oh, yes, makes sense, because pooling works on one layer at a time.
Yeah,
So it's
one feature
yeah,
at a time. Yeah.
Yeah, to add to that, you can actually like use only one layer, which will map, like you can flatten the output of the convolutional part, and then feed it to one fully connected layer, which will map it to the number of classes. But it just, I think, for example, in FastAI, they like empirically found some number of layers which works best. I think they have like 3 layers, like, or something like it's shown here. You can check out in the library. So empirically, it works better when you add this more fully connected layers.
So you're saying 3 fully connected layers are proven to be good fit for as FastAI guys discovered.
Yeah, they usually use ResNet as backend. Backbone, this full convolutional part, and maybe with different backbones, depending on your backbone, your classifier head may vary, but generally, I think that is what works. So,
if you remember, when we were doing the fine tuning, then we kind of get up to that point, like the third last layer, and then it's the new ones that are tagged on the end, so they do the fine tuning in FastAI. Do you remember that? No?
Yeah, say again. Yes, I do remember that you take the architecture for a transfer learning as is, and then you fine tune the final few layers. So are you saying we fine tune the fully connected layers again?
Yeah, those are the ones that they added when we did the fine tuning. They said they added the extra 2 layers at the end. I think it was 2 layers, yeah, or 3. I can't remember, but yeah, that was to handle the fine tuning for us. So I guess we get up to the third last layer there. That probably is where it stops, and those are the features. And then after that, you can do the fine tuning. That's what I understood from it.
Okay, that's very interesting.
Thanks.
At fine tuning, all fully connected layers are replaced, I think, in FastAI and in general. So.
Yeah, I don't remember if the flattened layer was there or not.
Yeah, flattening, I guess, is mainly needed for the 2D stuff. If it wasn't 2D, it wouldn't need it. Okay, so if we can move on to the so this is an implementation of a certain convolutional network. It's a convolution, a max pool, a convolution, a max pool, a flatten, a dense layer, some dropout to, and that's used to stop the overfitting. Quite high dropout, actually, 50%.
So one question on this, if you go up a bit.
Yeah, sure.
So here, no, down below on the code part. So when we apply convolutional 2D, it's a 7x7. What's the 64? Is it 64 neurons or 64 features it's going to create?
64 features is going to create.
Of a 7x7, you were saying, yeah.
Yes, it's going to be 64 features that will be created, but the kernel that will be applied will be 7x7 and of depth 1 in this case, because the input is only black and white. So the kernel will be 7x7 by 1.
Okay. Yeah. And then max pooling 2D of 2. That's a 2x2.
Yeah. So that's going to reduce the size of it, of the input by half. Actually, there's some padding applied because the 7, mind you, that no 7 would go into 28. So this will be a 14 now, because after the max pooling has happened, because it's stride 2, it'll be a 14 by 14. It will now create 128 features of 3 using a 3 by 3 by 64 kernel, because the last output was 64 depth. So at this point now, the kernels are going to be 3 by 3 by 64.
This 3 by 3 by 64. 64 is the depth. Okay.
Of the because the output from the last one was 64 features. The input to this guy is 64 features, and then the kernel that's going to be applied is 3 by 3 by 64, and so each kernel will be applied, that many times. Yeah, so it'll create 128 channels, but each one will have a 3 by 3 by 64 kernel applied.
So when we apply 3 by 3 by 64,
yeah,
after applying this, and then we have a 1 layer created out of it 128. So
yeah.
when we apply the 3-dimensional kernel, what does it do? It's average out, or because
No,
it's 3-dimension?
It's the same. It's the dot product. So the idea is that if you imagine that this kernel, the 3 by 3 by 64, is just like a cube of numbers.
Yeah,
it's just going to multiply the numbers in the features by this cube and then just add it together. It's a bit like a dot product. Yeah. Yeah, there's no averaging or mean. It's just multiplying everything together and adding it together. So multiplying it kind of pairwise. If you imagine, like, this 64 thing was 28 by 28 by 64 cube of data was what was output from this convolution.
Yeah.
And then in this one, the max pooling would have halved its size, but for a moment, if you ignore that bit, the next bit will be a 3 by 3 by 64 cube of data kind of working its way through each channel, through that lot. But there'll be 128 of them being done on that.
Right. Okay. And then we have the next layer. It's going to be 3 by 3 by 128.
Yes, that's right. Yes, because the previous layer had 128 outputs.
Okay. Yeah.
Yeah. And so this guy, even though it's quite a sophisticated, actually, I suppose if you go through it, so it says the first layer uses 64 fairly large filters, which is the 7 by 7, but no stride because the input images are not very large. It also sets the input shape as 28 by 28 by 1 because the images are 28 by 21 pixels with a single color channel, grayscale. Next, we have a max pooling layer, which uses a pool size of 2. So it divides each spatial dimension by a factor of 2. So that's this pooling layer. So now the image is halved, but you've still got that many channels. Then we repeat the same structure twice, 2 convolutional layers followed by max pooling layer. For larger images, we could repeat this structure several more times. The number of repetitions is a hyperparameter you can tune. So we've got 2 convolutions and then a pooling and then another 2 convolutions. Note that the number of filters grows as we climb up the convolutional neural net towards the output layer. So it's initially 64. So that we started with 64 when we first started, and then we went up to 128, and then we went up to 256. So we're sort of saying that by the time we finished, say, for instance, here, that we've detected 256 features in the input, because that's the number of channels that was the output of that layer. Okay, so we got 120. Okay, so it's initially 61, then 120, then 150. It makes sense for it to grow since the number of low-level features is often fairly low. For example, small circles, horizontal lines, but there are many different ways to combine them into higher level features. Yeah, so this is why he's saying that we use a lower number of channels right at the beginning, because the number of kind of features that we want to detect in the original input image may be low. For instance, we might want to detect horizontal lines, vertical lines, lines at various directions. But later on, when we want to detect hundreds of different objects, we need different we may have many hundreds of different features combined from those sort of more primitive features, and that's why the number of channels increases as you go deeper and deeper into it, in that there's more and more things to detect as a combination of what's actually in the image, rather than just directly, just looking directly at the image pixels. Does that make sense to people as to why this thing is growing bigger and bigger as we go deeper and deeper?
So it's the 64 are the features, and then when we jump into 128, so this is the combination of those 64 features, kind of like mixing together and coming up with more features. This is 128. And then again, when we go from 128 further on, so now it's mixing this 128 together to come up with the more features of 256.
That's right.
Yeah.
So we can imagine, say, we detected 64 types of lines, and then 128 types of lines from those shapes, and then 256 kind of actual components of the image from those 128 combinations of things. Yeah.
Makes sense. Thanks.
Yeah. Okay, so, and then says, it is common practice to double the number of filters after each pooling layer, since a pooling layer divides each dimensional factor by a factor of 2. Yeah, so he's saying, okay, fine, we're looking at these values, which is 64, 120, 26, but there's another thing as well, which is the size of the image as it's going through the network. And he's saying, because when we use pooling, particularly with the stride, we're compressing the image, we can increase the number of features and compress the size of the input to kind of roughly keep the same amount of kind of weight in amount of data. So that even though we're increasing these, we're not getting an explosion in the size of the data because of the pooling, which is kind of compressing it. So this is a bit of like expansion, we use the convolution, compression using the pooling, and then expansion via the convolution that you're having. Yeah.
What does he mean by a spatial dimension in our case? I understand what pooling is doing, but when he says spatial dimension, we are reducing or contracting the spatial dimension. What does a spatial means here?
So that's the size of the image that we're working on. So whatever, if it was originally, say, 28 by 28, that's the spatial dimensions of that image. As it's going through the network, convolution layers don't change the size of it, but pooling layers do. Well, actually, it depends on the stride, even the convolution, but normally all the convolution layers we have strides of 1, but the pooling is going to kind of compress that image that we're going to operate on.
Okay.
Yeah. And then he's saying, note that we must flatten its inputs so before feeding it to the dense network, because all dense networks expect one-dimensional arrays rather than working on two-dimensional images. So that's why we've got this kind of flattened layer here. So this is converting whatever the 2D shape was into a one-dimensional shape, which we can then pass down into the dense layers. So over the years, variants of this fundamental architecture have been developed, leading to amazing advances in the field. A good measure of this progress is the error rate in competition such as the IL-SVRC ImageNet Challenge. In this competition, the top 5 error rate for image classification fell from 26% to less than 2.3% in just 6 years. And it's interesting. So he says the images are large, 256 pixels high, and there are 1,000 classes, some of which are really subtle. Try to distinguish 120 dog breeds. Yeah, so we're getting performance, superhuman performance really on some of these tasks now. I mean, you'd have to be an absolute expert in dog breeds to be able to tell the difference between 120 different dogs. So yeah. So the first architecture, which was the famous one by Jan LeCun, is the Lenet 5. So some of the architecture in here is a little bit arbitrary because it was the very first one, and we hadn't kind of discovered some of the patterns to use in these kind of image classification, but it's worth knowing it because it was the very first one. Okay. So it's not a very deep network. So the input yeah, actually the images are 28 by 28, but they padded a little bit to make them 32 by 32 because the first kernel we apply is 5 by 5, and that doesn't go into 28. So we need the padding to be applied to that. Yeah, so the input is an image. We then use a convolution to generate 6 feature maps from that. We then use average pooling. We still leaves it at 6, but we use a 2 by 2 stride so that it halves the size of the image now. So by now the image is only 14 by 14. And then we create 16 features from that with a kernel size of 5 by 5. And this time, the resulting image size is 10 by 10 because 5 by 5 won't go into 14. So there's no padding here now. We're losing a little bit here. Then we're doing the average pooling with a stride of 2 by 2, which is reducing it up by half again. And then we're doing a convolution with 120 feature maps now, but the values are only 1 by 1 because we applied a 5 by 5 kernel and it was a 5 by 5 image. So the interesting thing here is that the whole image, which started out as 30 by 32, is actually been reduced to a single pixel. But it's got this depth of 120 because there were 120 features of just this one single value. So the overall data is not just by 1 pixel; it's actually 120 values is the output of the convolution operation here. And then that 120 is flattened to give you 120, and then you've got a dense network which has got 84 at this point, and then finally 10, which is what we're going to use to classify them. There's a slight complication in here. So yeah, so he's saying the 28 by the first comment is that the 28 by 28 was padded to make it 32 by 32. And the average pooling layers are slightly more, so the pooling layers are average rather than max pooling. The average pooling layers are slightly more complex than usual. Each neuron computes the mean of its inputs, then multiplies the result by a learnable coefficient, 1 per map, and adds a learnable bias term, again 1 per map. Then finally applies the activation function, which is tan h. Yeah, so the pooling is like quite a complicated one. It's not just average, it's doing something a bit more complicated. And the other thing he does is that the C3 to S2, so this convolution being applied to this guy, it's not connecting everything to everything. There's a table in the paper which says that only certain things are connected to certain things, and that must have been worked out experimentally as to what should be connected to what. It's interesting that they didn't just learn the weights. So at that point, there was a little bit of hard wiring in this model that there were only certain explicit connections which were learned. It wasn't just the whole kernel at the C3 level was learned, only some parts of it were learned. And then the output layer is a bit special as well. Instead of computing the matrix multiplication of the inputs in the weight vector, which is what you would have done, and then done a softmax on it, you're doing this weird calculation of the outputs of the square of the Euclidean distance between its input vector and its weight vector. Each output measures how much the image belongs to a particular digit class. The cross entropy cost function is now preferred as it penalizes bad predictions much more, producing larger gradients and converging faster. Yeah, so because it's the first one, it's got a few of these weird ideas in it, but they didn't survive in the long scheme of things. People have kind of simplified them down into using softmaxes and using fully connections between the convolution layers instead of this hard wiring of these wirings in this particular architecture. So I don't know, does anybody have any questions on that? It's a bit historical. It's worth knowing it exists, and it's basic architecture, but we don't really use that particular approach other than the fact that it's stacked convolutions pooling. Yeah. Is that okay?
Yep, fine.
And then the first of the modern ones, the first one is AlexNet. And it was developed by Alex Hrezevsky, I'm probably going to pronouncing that wrong, Ilya Sutskeva, and Jeffrey Hinton. It's similar to LeNet, but much larger and deeper. And that's the theme that we'll keep coming to. Things have just gotten much larger and much deeper as things have gone on. And it was first to stack convolution layers directly on top of one another instead of stacking a pooling layer on top of each convolution layer. So let's have a look at this architecture. So you've got an input, the bigger image now, 227 by 227. You've got a convolution and an 11 by 11 kernel. That's like a really big one. And then max pooling, a convolution, max pooling, but then a whole load of convolutions stacked one on top of another. And then a fully connected layer, quite a large one, 4096. 2 layers of that, and then a 1000 layer finally. And because it's classifying to 1000 images, because that's the size of the image data set that they were working on, that's where that 1000 comes. And I guess there's a softmax being applied at that point. Oh yeah, it is softmax there. And the validator and the activation functions are all really, they're not 10H anymore. So that's the kind of the basic architecture of it. So let's have a look. To reduce overfitting, the authors used 2 regularization techniques, which we're trying. First, they applied dropout, introduced chapter 11, with a 50% dropout rate during training to the outputs of layers F8 and F9. Yeah, so 50% dropout here and 50% dropout here. And second, they performed data augmentation by randomly shifting the training images by various offsets, flipping them horizontally and changing the lighting conditions. Yeah, so they're trying to make it more resilient, basically. And so there's a little bit of an explanation of what data augmentation is. So data augmentation artificially increases the size of the training set by generating many realistic variants of each training instance. Yeah, so this is something I'm quite interested in, actually. Because in NLP, I mean, I know for images, it's it's quite easy to imagine what you could do, but NLP is interesting as well, because sometimes the data sets are kind of small, so you need ways of augmenting them. So how they're doing this? The generated instances should be as realistic as possible. Ideally, given an image from the augmented training set, a human should not be able to tell whether it was augmented or not. Simply adding white noise will not help. The modification should be learnable, and you can't learn white noise. So even though you could add white noise and the humans would still recognize the same image, computers won't, because you can't learn random noise on top of data. So this kind of operation they're doing is, for example, you can slightly shift, rotate, and resize every picture in the training set for various amounts and add the resulting pictures to the training set. Yeah, so slightly rotating it, slightly shifting it, slightly changing the color on it, flipping it horizontally because potentially maybe you're looking at it from a slightly different direction. But yeah, I mean, we can all humans recognize that that's the same thing, and I guess and the computer should be able to recognize it as well. So does anybody have any comment on that? I think this augmentation thing is reasonably, not too difficult to understand. But I don't know. Does anybody have any comments on it? Because it is quite an important feature of this. Because it's just going to make the algorithm far more, the architecture far more robust, basically.
Okay.
Sorry, I had a quick question about not the data augmentation, but the table above. I'm not sure if they said what the padding equals valid meant. So I think same is just like you pad with zeros. Is that right?
Yes. So padding is, if it's required, pad it with zeros.
Okay. And valid means there's no padding?
Valid means that you're assuming there's no need for padding. But it means that if padding was required, you're going to lose. It's going to ignore that data. I mean, for instance, let's say this was 50 by 50, and you had 11 by 11 kernel. If you required it to, if it was the same, then I guess 11 by 11, it would have to be 55. So that would add a padding of 5 to it. Whereas if it was valid, then basically it would only take the 44 by 44. The other 6 pixels would just be dropped because the data was assumed to be valid. And if it's not, that's your tough luck. We're going to ignore the pixels that we can't cope with because the kernel's of size 11 by 11. Does that sort of make sense?
Yeah, I guess that makes sense.
Yeah. Yeah, I mean, valid just means we're going to assume you did the right thing, and if the data doesn't match, we're just going to ignore the bit that doesn't work for us. And same is we will actually convert it to be as is required by the kernel that we're using. So it's the same as the kernel.
Okay.
Yeah.
Thanks.
Okay, cool. And yeah, they've got this really weird normalization step. It's easy to understand what they're doing, but quite hard to work out from this formula what the hell it's doing. So AlexNet uses a competitive normalization step immediately after the ReLU steps of layers C1 and C3, called a local response normalization. The most strongly activated neurons inhibit other neurons located at the same position in neighboring feature maps. Such competitive activation has been observed in biological neurons. Yeah, so what you're doing is, if so we're looking at C1 and C3. So between this guy and this guy, what we're doing is if you're looking at a particular feature map and a particular neuron within it, whatever, when something within C3, is being computed, high values of that neuron activation cause other values within C3, slightly above and below in this stack of features, to be kind of pushed down, as it were. Does that kind of intuitively make sense what it's doing? It's sort of like a bit of competition. If I'm slightly strongly activated, anybody close to me will have to be, would have to be slightly more lower activated than it would have been if we'd not kind of made any change. So there's a little bit kind of winner takes all type mentality in this, in this kind of calculation. As I say, it's got a few kind of hyperparameters in there that control how strongly the neighbors are suppressed in here, and they give the hyperparameters that we used in AlexNet here. And interestingly, so AlexNet won the competition in 2013, I think. So when we did AlexNet win? Yeah, in 2012. And a variant of it which used different, okay, and then a variant of it which used a different, let's have a look. And a variant of AlexNet was developed by Matthew Zeal and Rob Fergus, won the 2013 one, and it essentially just tweaked the hyperparameters of the AlexNet. So, and I wonder if they changed some of this the normalization function parameters of it, but I must confess I haven't seen the paper. So does anybody have any questions of that? I haven't really gone through this formula because I don't really fully understand it, and I'm not sure I totally agree with what some of these values are in here. But intuitively, I can sort of understand what it's doing is, there's a little bit of dynamics in here. You're looking at a particular value, and then you're biasing the neighbors of it in the stack of features. So it's not within the same kernel, it's within other features, the kernels that are near it, up and down, above and below the current feature in the stack. This is where this high and low bit comes from, because there's this notion of a radius. So when you're looking at a particular feature and a point, you're only looking at within this radius of it to have an effect on the others. Yeah, I don't know if anybody had any questions about that one. I know I've now made a good explanation of that.
I was quite interested in that because it's the first time I've actually seen that, which is quite strange considering that, we've been looking at these kind of networks for a while now. We haven't used this, like, okay, I don't know, in FastAI I don't remember seeing this kind of thing, but it sounds like we're like locally trying to boost one of the weights and like suppress the ones around it, whereas most of the time we're trying to prevent that kind of thing. So we're trying to add regularization, stuff like that. So I'm not sure why suddenly we're interested in boosting. Or did I misunderstand that?
Yeah, so I mean, I guess it was found experimentally, but they are saying that you do see it in biological neurons, that a neuron activating actually suppresses neighboring neurons. So you're sort of amplifying that particular signal, as it were. Yeah, I must confess I hadn't come across it before until the guy mentioned it on Sunday. Okay. And I haven't had a really good chance to look at whether this is used more globally than other than this particular architecture at this point in time.
So as I understand what it does, it forces like this neighboring kernels to learn more dissimilar features, like the more distinct features, right?
Yes, yes.
Okay. So it's trying to prevent them from being too similar. Oh, okay.
Yeah, yes, I mean, it would have that effect. Yeah, if I'm activated, don't activate at the same time as me.
Oh,
But if
okay.
you want to activate at a different time, then that's fine. Yeah.
Okay. Yeah, that sounds more interesting. Okay, cool. Thanks.
And I think we've come to about 7:45 now. So we might start because this is roughly, although I don't know if you guys want to just, yeah, because they went up to ResNet, didn't they? The Google LearNet architecture is very similar. The only thing is that all the kernels are much smaller, but there's like it's a lot deeper. But one of the nice effects of that is that AlexNet actually has 60 million parameters, and Google LearNet, which actually performs better, only has 6 million parameters. And so this is kind of like the advantage of using much smaller kernels. But they have got a special thing called a depth concatenation layer, which is a kind of a weird, I'm still trying to get my head around what a depth concatenation actually does. But this is kind of an inception module. I don't know if you'll just spend a couple of minutes just mentioning this one, because this is really the core of it. So, and you can stack these inception modules one on top of another, because the size of the input and the size of the output is the same, because all the strides are one in here. So there's no compression and expansion happening.
I think it says the depth concatenation is just stacking the feature maps from all four of them because they're the same dimensions,
Yes.
So you can
So I guess it depends on how many channels there are. But yes. So if that was 3 channels and this was 3, this was 3, this was 3, then the total would be 12 channels.
Oh no, spatially, right? They would have to be spatially the same, so you could stack them to. Right?
No, but what I mean is, if I mean that's a 1-by-1 convolution, but if the number of features it was detected was 5, and that was the depth of it, and the depth of this one was 3, and this was 2, and this was 1, then the overall depth would be that one, that one, and that one, and that one, all kind of added together. It's almost like what this thing is doing is saying, okay, you detected these features, you detected these features, you detected these features, you detected these features. I'm just going to concatenate them all up in as the set of all the features that were detected by the inception module. Yeah. Or do you disagree with that?
Oh no, I'm just reading that bit again. Just above that picture, it says all their outputs have the same height and width as their inputs. But I don't know if that's just the first.
So there's 3 different things here, isn't it? There's the height and width of the input, which is the spatial dimensions, and then there's the depth, which is the number of feature maps. Yeah. So what I'm saying is, yes, the spatial dimension, the width and height is all going to be the same because all the strides are 1.
Oh yeah. Then it should.
But then the convolutions, the number of features that they're detecting will be different.
Oh yeah.
And I think what that guy is doing is just concatenating all the different features and outputting that. Yeah,
that's what I understood.
Okay. So that's kind of like an interesting thing.
So are they like somehow they're going in parallel, or they stacked? How they are stacked? What's the difference? For example, what's the difference between in a middle convolutional 1-by-1 plus 1s and then one down below?
So imagine each of these kind of arrowed sides are parallel. So for instance, there's one going that way, that's parallel. There's another one here, which is parallel, and there's another one here, which is parallel, and there's another one here in parallel. And then all those features that these guys computed are then kind of concatenated together like one big stack of them, and that's the output.
Okay.
And so the interesting thing is that, you know, so there's a little comment in here saying, well, it seems like the one by one stride is not actually doing anything. But he's saying, well, okay, fine, it's not, might not be doing a lot for you on a particular horizontal, like, you know, on a particular image, but actually there's a depth to that as well. So it could be that there's like information in the depthness of it, not just on the, you know, the fact that it's one by one, because you have to remember this is 3-dimensional. It's whatever's happening on the image is a one by one, but then there's like, there'll be 50 of them because you had a channel, 50 channels, say. So there is actually stuff happening in the depth direction, which is interesting. And
what's the +1 S in a bracket stands for?
that's the stride.
Oh, stride. Okay.
Yeah, it's interesting why they mention it, because they're all one anyway, so they might as well not bothered saying. They could have just put here stride 1.
Am I right in thinking that the output, like before the concat, is the same, not because the stride is equal to 1, but because like we're padding different convolutions differently so that the output is the same at the end. So like, for example, the 1 by 1 plus 1 stride convolution doesn't need any padding, whereas like 3 by 3 plus 1 stride will need a little bit of padding, maybe like 2 or something on each side, or maybe 1 on each side. Whereas like the 5 by 5 plus 1 will need like two rows of pad. Do you know? I think that's why
that's
they're the
an
same.
interesting point you bring up, and I guess, yeah, I mean, some of these are prime numbers, so I'd be surprised if the padding wasn't required. But yeah, that's a good point you bring up. But I'm assuming the way they've done is somehow because the output is still, they're all the same, so that whatever padding was required.
Yeah, sure. Otherwise, you wouldn't be able to concat, right?
Yeah.
Sorry, Arto.
I was saying you just use same padding for each, and so when you use same padding.
Okay.
Yeah, but
okay.
Arto, not necessarily, because let's say the image was 32 by 32. Well, 5 by 5, that would need padding, but 3 by 3, you wouldn't, because 8 times 3 is
yeah, we're doing convolution with stride of 1, so it will for each location it will output. We shift 3 by 3 filter by 1 pixel every time. So it, for example, 3 by 3 convolution without padding would reduce the height and width by 2 or by 4, right?
Yeah.
By 2, I guess. And so, and 5 by 5 would reduce the height and width by twice as more as 3 by 3 would. But if you add like 0 padding everywhere, with this same padding ensures that the output of the convolution has the same height and width if you have stride of 1.
Yeah.
If you have if you would have stride of 2, it would ensure that you reduce by 2.
Yeah, so there is a description of it.
Sorry, are you suggesting that the same means we pad with 0 so that the input and the output are the same size?
Yeah, right.
Okay, gotcha.
Yeah, not necessarily you have to pad with zeros, but you add the amount of padding which is necessary to have the same size.
Right, gotcha. Yeah, that makes a lot more sense. Thank you.
Yeah, so I guess it's also it's kind of a little bit hardwired in that it's meant to handle images of a certain size because it's working on a particular data set. Although having said that, didn't they mention that Google's one could work on any sized image, because these guys, these inception modules, there's no
yeah, it can work on any size of image because they use global average pooling or global max pooling or whatever global pooling.
Oh, okay. Yeah, interesting. Yeah, but it was an interesting point you made, Maria, because like I hadn't thought about how the padding would impact, because there a few of these kernels are different sizes. But I guess so long as the overall architecture, the way the inputs were kind of before they got to the inception modules, if they were kind of in the right kind of shape, then you wouldn't have a problem with stacking all the inception modules one on top of another.
Yeah. Actually, there is a pretty simple formula how you can compute the output dimension height and width of the convolution. You have this input dimension. You subtract kernel divided by 2 and add padding and divide by stride. If I'm not wrong, something like that. So if you look at that formula, it will like become pretty simple. How much padding do you need to add if you want to preserve input height and width?
And this is the overall Google Linnet architecture. So from input, so convolution, max pooling, local response normalization. Oh, interestingly, Google Linnet uses local response normalization as well, and it uses it in twice. Max pooling, then a whole load of inception modules, so max pooling, whole load of inception modules, max pooling, inception modules, a global average across 1 or 2, 4 features, dropout, fully connected 1000, and then softmax. And I think, so that's the, don't think I had any other comments. Yeah, and I think the guys just got to VGGNet, so I guess and ResNet they're going to pick up on Sunday, because I don't think they really did ResNet, did they?
No, they didn't.
Yeah.
We stopped at VGG.
Yeah. So I think we'll probably stop there as well. Does anybody have any other questions? That I know we rushed through the Google Linnet a little bit. It's a shame. Fortunately, time's always tricky.
Not questions, but I just wanted to say I mean, I think a lot of us have covered CNNs a lot, but there were some really interesting things there, like the local response normalization was new for me and interesting. And then also just further down Google and Net, they said they also had 2 auxiliary classifiers. That was also interesting. So yeah, that's probably, might be interesting to look at that paper.
Yeah, I think for those, about those 2 auxiliary classifiers, I think they couldn't train such a deep network without skip connections. So they had to like add intermediate loss to help lower layers train.
Okay.
So, but that's what I guess how it worked. That's
okay. Yeah. Interesting. Okay. Yeah. Okay. It says down here the goal was to find the vanishing gradients problem. Wait, where is that? However, it was later shown that the effect was relatively minor. Is that the same thing?
Yeah, the
okay.
vanishing gradients and the exploding gradients would be what you would need. That I mean, that's why ResNets, I guess, the residual connections help, but they weren't invented when these guys were created this.
Just thinking about all the work that goes into these architectures. It must be taking them ages to develop the first few. Sheesh.
Yeah, I mean, it's crazy. I mean, look at all that.
Yeah. Okay. Cool.
Yeah, so I guess the guys will pick up on ResNets on Sunday, and and we'll be back next week. Yeah, if we have time, maybe we can look at that local. And what was the name of the thing called? The local response normalization. Yeah, the local response normalization. I don't know if anybody's interested enough to find out more about it and tell us.
I'll give it a shot.
Yeah, that would be great, Parisha, if you could. Because as I said, I hadn't come across it before, and it looks interesting.
Cool.
Cool. Well, I'll let you guys go because it's 8 o'clock already. I know you're probably exhausted by now. I know on the Sunday one, it was an hour and a half. I was like really struggling near the end.
Great. Thanks, Arshad.
Yeah.
Yeah.
Have a nice week, guys. I'll see you on Sunday.
Yeah.
Yes.
Right.